Hi and welcome back. In this video I'm going to tell you about use cases of the Riemannian optimization in quantum technologies. And at the beginning I will discuss use cases of Stiefel manifold, complex Stiefel manifold. But before diving into details of applications, it is useful to introduce special notations for tensors that are called Penrose graphical notations. We represent tensor as geometrical figure such as circle or a rectangle or square. Indices of a tensor we represent as free edges. Convolutions between indices of a tensors we represent as connections between edges. For example, on a given slide you can see different graphical representations for basic operations with matrices and tensors. In quantum technologies, we very often consider so-called quantum programs. A quantum program is essentially a sequence of unitary transformations that are connected with each other. For example, on a given slide, you can see a quantum program that is represented in terms of Penrose graphical notations. This quantum program consists of local unitary transformations that have one input index and one output index, and two qubit unitary transformations that in a particular case take form of C0 gate that is defined on a slide. Quantum program has input where you can pass some quantum state and output, which is a result of application of a quantum program to a quantum state. We can use quantum programs for different purposes. For example, we can use them to prepare a desirable quantum state. Let us assume that we pass some trivial state which can be easily prepared in a quantum hardware through a quantum program. And we get some output state that is a result of application of a quantum program to an input quantum state. We can adjust local unitary gates in order to achieve some desirable quantum state. It can be done, for example, by maximizing quantum fidelity between desirable quantum state. On this slide, desirable quantum state is represented by psi true, and output quantum state. Since local unitary transformations are elements of a manifold, that is a special case of Stiefel manifold, one can use Riemannian optimization to solve this problem, to maximize quantum fidelity. As you can see on a slide, the difference between theoretical maximal value of a quantum fidelity and actual value of quantum fidelity drops rapidly towards zero value, and after this optimization process we have a properly prepared desirable quantum state by adjusted quantum program. We can use Riemannian optimization to optimize different kinds of quantum programs. For example, by application this quantum program to some trivial quantum state, we can achieve maximally entangled quantum state via maximizing entanglement entropy between subsystems of a output quantum state. We also can use quantum optimization to decompose quantum program into a sequence of local unitary gates and C-nodes. In a particular example, as a quantum program, we consider simple 2-qubit unitary transformation. We can solve this problem, for example, via minimizing Frobenius distance between quantum program and its decomposition. We can use Riemannian optimization on the complex Stiefel manifold even for more fundamental problems like characterization of quantum materials and their phase transitions. You can read more about such techniques and application of Riemannian optimization to this kind of techniques in the following list of papers. Now let us consider use cases of density matrices manifold, and the most straightforward and obvious application of the manifold of density matrices is tomography of quantum states. Let us assume that we have an experimental setup, and this experimental setup contains quantum system with unknown quantum state, and we want to reconstruct the state of a system. How can we do that? For example, we can do the following. We can prepare several copies of an unknown quantum state, then pass these copies through a measurement device and end up with results of measurements. Then we can use these results of measurements to reconstruct the unknown quantum state. For example, we can maximize logarithmic likelihood with respect to unknown density matrix. And unknown density matrix has standard constraints that can be satisfied by Riemannian optimization tools. Here you can see some pieces of results. We perform 600,000 measurements and then perform quantum tomography by using Riemannian optimization. Y-axis shows distance between the unknown quantum state that we want to reconstruct and its reconstruction. X-axis shows number of iterations. One can see that after this optimization process, we have a good estimation of the unknown quantum state that well agrees with other types of quantum tomography of states. Let us discuss now use cases of Choi matrices manifold, and again the most straightforward and obvious application of Choi matrices manifold is quantum tomography of quantum channels. Again, let us assume that we have a quantum setup, we have an experimental setup with unknown quantum channel. And we want to reconstruct this quantum channel. How can we do that? For example, we can prepare a set of input quantum states, then pass these quantum states through the unknown quantum channel, then pass output states through some measurement device and end up with measurement results. Then, in order to reconstruct the unknown quantum channel, we can do the following. We can maximize logarithmic likelihood, the following logarithmic likelihood, with respect to Choi matrix that parameterize the unknown quantum channel. And Choi matrix again has standard constraints that can be satisfied by Riemannian optimization tools. Now let us consider some pieces of results. Again, we perform 600,000 of measurements and end up with the following plot. Y-axis shows distance between Choi matrices. X-axis shows number of iterations. As you can see, at the end of this process, we have good estimation of an unknown quantum channel or Choi matrix that well agrees with other types of quantum channel tomography. We can go even beyond optimization on manifolds and use sampling methods on manifold in order to, for example, reconstruct posterior distributions in quantum tomography. There is an experimental implementation of manifold Langevin dynamics in our library. As a conclusion, here I show the list of applications that we can suggest for now. It is machine learning with unitary tensor networks. It is different quantum control problems. It is identification of unknown open quantum system. It is tomography of quantum states and channels, analysis of many-body quantum systems and their phase transitions, adaptive tomography, and combinations of different approaches like it is done in deep learning. And that's it about applications of Riemannian optimization to quantum technologies, and thank you for your attention.